how do you make this experiment fail? How do you make the Ohm's law holds true? What are the things you can change so that the Ohm's law will be true? Can you change just one thing, then the Ohm's law will be true? Say it again? Frequency. How do I change the frequency? Make it 0, right? Okay, can you change it very low? Can you change it to about a few kilohertz? You can see the light, the lamp started to turn on. Okay, what's the frequency now? 1 megahertz. Okay, we didn't change it to 0. We changed it to 1 megahertz. Can I borrow your key again? Now, what's going to happen if I? Now, what's going to happen if I turn it? It's okay. The source has a 50 ohm there. It's not going to be burned, right? It's not a battery. Is this a good one or a bad one? Is this a very cheap one or expensive one? Very expensive. Yeah. Now I'm going to try it. I don't think it's going to be burned. Now this is really a short circuit, right? Okay, what's the wavelength of 1 megahertz wave? It's 200 meters, right? What is this compared to 200 meters? It's almost 0, right? Okay, so basically, if you think about from the wave propagation point of view, this is your wavelength. It's 200 meters, right? Then I'm looking at 1 meter cable. Now we can see that at the two ends of the cable, the voltage is the same. Is that true? At the two ends of the cable, no matter when you check it, the voltage at this end and this end is the same. Now Ohm's law, it would be correct, right? So to make sure the Ohm's law assumes at anywhere along the line, you have exactly the same voltage, right? That's when you can use Ohm's law. But if your line is too long, it's very long. If I have a 200 meter line here, the Ohm's law definitely is not going to be true, right? You have 0 voltage here, and then maximum voltage here, 0 voltage here. You can see the voltage along this line is not constant. That's the key. That's the key point. Okay. So basically, how do we know when to apply Ohm's law, when to use transmission line theory? It's basically if your line is very short. The word short is pretty hard to pronounce, and also you have to pronounce it from here. Short. That's American pronunciation. It's short. You have to use your deep voice. Short. That's how the Americans pronounce this word. Okay. So, and that line length is not the absolute length of the line. It's a comparison, right? It's a comparison. Whether the line is short or it's long is compared to the wavelengths, right? Compared to 200 meter wavelengths, this is very short, right? Compared to that 5 meter wavelength, this is pretty long. It's 1/4 of that. Okay, so that's the reason that we have to deal with this transmission line is assuming if your wavelength is 1 gigahertz. Okay, frequency. Sorry, if your frequency is 1 gigahertz, what is wavelength? If you're still being 60%, then wavelength becomes, what is the wavelength? is about 20 centimeters, right? Which is about this long. If this is your wavelength, your printed circuit board is a very long line, right? If they sell a printed circuit board this big, that's one wavelength long. That's a big board. That's why when the frequency is very high, and all the printed circuit board, they all become transmission lines. Okay, and that's why we need to study transmission lines, because and a gigahertz signal is very common right nowadays. Okay, all right. So this is what I want to talk to you about, a concept and theory, and then I have a lot of mathematics. I will go through this very quickly. Okay. Okay, this is simulation of transmission line. This is the 3D field simulation from a software pack, a simulation for software. Okay, and this is you can see this is a very short. It's a very short line because the current. This is the field, and this is H field. A over M is H field. Okay, you can see it's almost the same along the line, right? Okay, when they are bigger, it's all bigger. When they're longer, they're all longer. Higher is all higher. So this is a very short line. When the line is short enough, we just assume it doesn't exist in the circuit theory. In circuit theory, we assume line have no length, all just components there, right? Okay, but if you look at this line, that's very long. Okay, you can see that the H field is changing along the line. So you cannot assume the H field at this point and this point, or the current at this point and this point are the same. They're not the same. Okay, so this is the transmission line, and again, this is also a transmission line where we have an open load. This is the source here. That's a load. So at load end, there's no current, right? But there's a current is over here. There's a lot of currents here. Okay. Again, this is a short load where you have a maximum current here. And this line is much longer. You can see there it's about 3/4 of the wavelength, almost a complete wavelength. Okay, so you can see that you have a lot of currents here. There's almost no current there. There's currents here. Okay, that's transmission, wave propagation. Okay, this is a much longer line. It's 2 wavelengths. Okay, this line is 2 wavelengths long. You can see that this is 1 wavelength, and that's another wavelength. So it's a very, very long line. Okay. All right. Okay. So how does wave propagate through? Let me switch this up. Through this transmission line. Okay. Wave propagate through this transmission line by electric field and magnetic field interchanging. Okay, so I'm going to explain this concept, and then we'll take a break after this. Okay, this is exactly what Zheng Yuquan, you mentioned that how come this voltage is constant, this voltage is not constant? Okay, because we actually we assume this is constant, then we can calculate voltage from E times distance. Okay, that's how we can get voltage. So how does wave propagate? Let me explain to you a little bit. And this is very interesting. I really like this theory very much. Okay, so if I have a piece of transmission line, okay, let's say I'm assuming 2 lines. Okay. I have another marker. Let's try this one. Okay, if I take a snapshot of this line, if this is my voltage, okay, if this is my voltage along the line, and then what is the charge distribution over here and over here? Can you draw charge distribution along the line? Can you draw charge distribution along this line? Do we have positive charge here or negative charge here? Assuming this is voltage, this is positive voltage, right? This is 0 volt here, and this is negative voltage. What is charge distribution here at that time instant? We're going to have positive charges here, right? That's why we have that voltage. Okay? On this end, we're going to have negative charges. A lot of them, because that's how E field is generated. And then if you have distance here, that E times D will give you the voltage, right? So you must have a lot of charges to generate that voltage. Then you have less charge here, and then less charge here, and it's almost no charge at the end, okay? Because this voltage here is 0, okay? There's no charge here. What about this end here? We're given negative charges on top, right? And then positive charge here. This is one snapshot, okay? One snapshot. Assuming the wave is propagating through in this direction, this is wave direction, okay? This is wave direction. All right. Now, if we let the wave move, okay, we freeze it, we let it move. What's going to happen if I have a positive charge here, negative charge here? What's going to happen if I let it go? What's going to happen? Because this is a conductor, right? What's going to happen here? They're going to be attracted to each other, right? So you're going to generate charge movement. What is charge movement? Current. Okay. Current is another word. We Chinese do not pronounce it very well. Okay. See current.
Current.
Okay. The American will see current. Current. It's pronounced from right here. You know, when we speak Chinese, we use our lips a lot, right? So we basically make sounds from our face right here. When you speak English, you try to use your chest as much as possible. So we'll see current, right? Current. Actually, if you listen to Americans, they will say current. Just push your voice as low as possible into your chest. Current. Okay, let's see you. Yes. Say it. No. Current. Like short. Say short. Yes. No. See, can you tell the difference? Say it again. Yeah, it's a little bit more. Just yes. Short. Okay. Basically, the sound comes deep in, right at here, and then almost from your chest. Short. See it? See, you make, when you see short. See, the sound is from your mouth, right? The sound should be from your short. Yes. Okay. Anyway, so current is going to start. Of course, the current is going to start from this direction. Whenever we have a current, what else do we have? Magnetic field, right? Whenever we have a current, we have magnetic field. So how does magnetic field generate? It's going to be like this. That's H field. Okay? So if the energy is moving in this direction, okay, so you're going to have another H field here. Okay? That H field is going to move charges. Okay? So that then it's going to generate an E field, because H field is going to generate E field. The time changing H field is going to generate E field. Okay? So that's how energy is propagating. This is E field, this H field. Okay? So energy is propagating through by interaction of E field and H field. Okay? And of course, mathematically, we can describe this as crosstalk product of these two. And this is a vector. What is this name of this vector? Pointing vector. That's a pointing vector. Okay. And that's how pointing vector works. Point. Again, when you say point, you can use the point. Yeah. So don't try to use the lips. Okay. When you speak English, your lips will not make any sound at all. Okay. Don't speak like the people in Shanghai. You know how they do, you notice how they speak. They talk. They'll say, it's just lip movement, nothing else, right? Okay, if you do, yeah. Okay, so that's how. Okay, now another concept. Okay, when we most time when we discuss circuit theory, okay, we see, all right, this is the source. There's a source resistance, and then there's a load, and so this is this voltage source. Okay, there's a load, and then the current goes from here and then returns from here. Is this correct? It's like a water pipe, right? It's like water pipe. The current goes in from this top, goes through the load, and comes back from the bottom. Is this correct? Yes or no? Yes. No. It's not correct at all. See how energy propagate? As soon as the current is generated here, I don't want to pronounce current like current. I always want to say current, which is wrong. But I'm used to it. I always say current. But Americans do not understand what I'm talking about. Okay. You have to say current. Current, then they will know. So I'll try to do that. Current. Okay. So as soon as this current is generated, this current is going to generate at exactly the same time. Okay? So the energy actually propagated this way to hit the load. It's not like water pipe at all. Okay? You can see that because the H field is here and E field is here, so it will generate at the same time. Okay, the return, this is return. This is another word. Say return. Say it again. Return. 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 Yeah. That's another word. Okay. All right. So this is the incoming. This is the incoming current. This is return current. They will be generated exactly at the same time. Okay. And then the wave will propagate this way. They will reach the load at the same time. Okay. So that's the difference. The difference doesn't matter if you assume this is very short, right? If it is short enough, they will appear at the same time anyway, right? But if it's long, you still assume, oh, there's a current here, but there's no current here. That's the wrong concept. Exactly wrong concept. Because electrical energy propagates through, okay, basically if you think about the battery, okay, as soon as positive charge appears here, what's going to happen here? Negative charge will appear right away, right? So it's not going to wait until positive charge moved here and then negative charge is going to return. That's not true. Okay, that's not true. So because this is the E field, it's a charge separation, so they will appear at the same time. Okay, that's another concept. So the two concepts here when we talk about transmission lines, one is Ohm's law does not apply because the voltage on the two ends of the line are not the same. Second concept is energy propagation is through both lines, just like Zheng Yuqian asked a question about why there's nothing on this line. There is something on this line, okay? And it's just, as soon as you assume this is zero, so that this voltage can be higher or lower compared to this line, okay? So both lines are contributing to the energy propagation, okay? That's a lot of concept, and then let's take a break, and we'll continue from here. Okay, let's take a break.